So the objective of this video is to provide an overview of what we'll be going over in the course, along with giving you some information about the grading policy for our course. So like always, this information is contained in more detail within the course syllabus, which I'll show you how to access during the week 1 intro video. However, I do want to kind of provide the basic summary information that at least when I was a student that I always cared about. So first and foremost, we'll begin with the learning outcomes. And this is really important because these are things that actually can't be dictated by your instructor. We have to teach to these learning outcomes, and I'm sure that many of you have taken kind of more challenging engineering and physics classes beforehand, particularly in an accelerated environment. Sometimes it's hard to get through all of the learning outcomes in an accelerated course. So since we only have 8 weeks, and at least when I took this course, this was a kind of content that was presented over 20 weeks. We took on a quarterly basis DC circuits and AC circuits separately. My approach is going to be to make sure that we hit all of these, even if it means we can't go in as much detail about any particular one. So just reviewing these, learning objective 1 is just giving you a basic understanding of SI units, engineering notation. I'm sure for the majority of you that will be review, along with the fundamental kind of electrical quantities of charge, current, voltage, power, and energy. So especially for those of you that have had the intro to engineering course with me, hopefully learning objective 1 will be a total review. Learning objective 2, applying the concepts of electric network topology, nodes, branches, and loops to solve circuit problems, and including the use of computer simulation. So you'll see that on the actual module for this week, as discussed in the week 1 intro video, one of the things that you need to do if you haven't done it yet is actually set up access to a multi-sim live account for the actual computer simulation portion of that. And what you'll find is that really these ideas of nodes, branches, and loops are really just one of nomenclature. Once we've introduced the fundamental circuit components and talked about their actual schematic representations, we will see that really it's just something you can pick up pretty quickly. Topic 3, analyzing circuits with ideal, independent, and controlled voltage and current sources. If you've had me for the intro class or maybe in your physics class, of course, you ideally have already seen an independent voltage source. However, the idea of a dependent voltage source or a dependent current source is exactly what it sounds like. It's just that the voltage produced across the terminals or the current actually passing through the terminals is determined as a function of some other quantity within the circuit. So oftentimes these are useful for modeling things, particularly transistors, for those of you that are going down the electrical and computer engineering pathway. 4, applying Kirchhoff's voltage and current laws. You might have heard of those by their acronyms, KVL and KCL, to the analysis of electric circuits. I would say if I were you, if you had me for the intro course, 1 through 4 is going to be largely review. Going to step 5, explaining the relationship of voltage and current in resistors, capacitors, inductors, mutual inductors, and other circuit elements. Those are just the basic VI relationships that we also introduced, at least for a resistor in intro, namely that the relationship between voltage and current within a resistor is just a linear function described by Ohm's law. In a capacitor and inductors, you start to see the duality of electricity and magnetism, and the IV relationships there are actual differential equations. So moving on to actual learning outcome 6 here, derive and solve the governing differential equations for a time domain first order and second order circuit, including singularity function source models. Sounds really, really complex, but not really. If you have a basic RC or a basic RL circuit, what you find is that those are very simple first order differential equations whose eigenfunctions are simply those of exponential decay. So in your physics class, probably you've seen how an actual RC circuit works when it's charging, and once it's charged, that current is basically exponentially decaying to 0 with a time constant that's determined by the particular component values within the circuit. So sounds really complicated, but not too much. Even if you haven't taken differential equations yet, or you're taking it in parallel, we will introduce the content that you need in a just-in-time framework. 7, describing the Thevenin or Norton equivalent of a given network that may include passive devices, dependent sources, and independent sources in combination. Big idea there is, do you have a technique that can simplify any complex circuit into a very simplistic circuit consisting of only a source and 2 elements in series, or kind of a voltage divider network? That's the idea for a Thevenin equivalent circuit. Norton is basically the dual kind of framework of that ideal from an actual current source point of view. That might be one of the things we skip a little bit, or at least don't give you problems on, but just introduce if we don't have a lot of time. 8, analyzing first and second order AC and DC circuits for steady state and transient response in the time and the frequency domain. A little bit of that was kind of implied in learning outcome 6, I should say. Oftentimes, as is the case here, these are not perfectly linearly independent learning outcomes in this case. But the important thing to note in 8 there is you're kind of transitioning from analysis in the time domain to the frequency domain, which is kind of moving from DC circuit analysis to AC circuit analysis. 9, deriving relations for and calculating the gain and input impedance for an op-amp circuit for both DC and frequency domain AC circuits using an ideal operational amplifier model. So that is kind of moving into a little bit of active circuit analysis, but it's actually abstracted to a level that it's pretty easy to understand, as you'll see when we get to that content. And that actually comes before we're going to really hit op amps hard before we move into the AC circuit portion of the course, which will be in that, I believe, we'll look at the schedule here in a minute, that the op-amp content actually comes around the midterm week. 10, applying computer, mathematical, and simulation programs to solve circuits. We're going to use Multisim as kind of our circuit analysis solver. I'm also going to have you download MATLAB if you haven't already. I shouldn't say download, but set up a MathWorks account. If you want to use MATLAB online, that's fine. If you do want to download it locally to your machine, that's totally okay. But everything that we'll do in this class, you'll be able to do with only MATLAB online. And the reason for that is I think it's good to see kind of some numerical simulations of the governing differential equations for the circuits we'll be considering in this class. And then 11, analyzing circuits using the Laplace transform, or just the S domain, which is really an approach that engineers often take, where you have these circuits that are governed by relatively complex differential equations, and through using transforms, we're actually able to express the solutions in an algebraic framework instead to make our lives easier. So I do have a course schedule up for the course. I'm going to keep it on this Google Sheet just to make it a little bit dynamic. After we get done with the lecture, I'll pull that link and put it in the browser and we'll look at it. Unfortunately, some reason when I try to link directly from PowerPoint, it's telling me that my Chrome needs updated. So if you run into the same issue, just right click and grab the link and paste it directly into your preferred browser. So as you saw in the Start Here announcement, I'm going to push out contents on Mondays and Wednesdays, and that is really just intended to keep you engaged with the course in multiple times throughout the week. You're going to find it really hard if you wait till Saturday or Sunday and try to do all of this, because some of these concepts are a little bit abstract and it just takes a while for them to settle in your mind. So believe it or not, the same amount of time spent either spread out during the week or just on the weekend will go so much better if you spread it out during the week. Even if you can't do it every day, just pick a day or two and try to engage with it an hour or two. And when you get to those homeworks being due on weekends, I think you'll find that they're a lot easier because those concepts and the terminology and the nomenclature have had time to kind of crystallize within your head. So what I'm saying here is the lectures may only cover a subset of the overall course material in order to focus your attention on the most important concepts for homeworks and exams. If someone went in detail of all these learning outcomes, there's just no way. I mean, the human brain, right? It has certain limitations with respect to how quickly it can absorb this content, even if you have adequate background knowledge from a kind of electrodynamics physics course. All of these outcomes, it would be really, really tough, even if it was the only thing you were doing and you were spending 10 hours a week on it or 15 hours a week on it. To pick them up in like 10 weeks. So we're really going to be pressed for time. So my kind of approach for this is make sure that everyone has a strong foundational knowledge of a subset of this material, and anything we don't get to go over, like any particular nuance of a topic, if we can't do a detailed example of it, just to kind of make sure that you're functionally aware of how the examples that we did could be generalized to those new problems. So we do have an assigned textbook. It is not yet integrated within Canvas. That, I'm sorry, is not my fault. It was an issue on the publisher's end. In addition, we're going to be using Connect for homework. That is not set up either. That's why when you look at the schedule, you'll see that the first homework assignments for the class are actually not due this Sunday, but they're due next Sunday, just in case that ends up taking a few days. In addition, everything is going to be due on actual midnight of the week that it's assigned in general, other than this week because of that issue with Canvas. Even though you're turning a lot of stuff in Connect, I am occasionally going to ask you for some additional stuff that actually involves maybe a little bit of scripting in MATLAB or simulations in Multisim. If you want a standing office hour, I will always be available for questions from 6 to 7 via Zoom. However, if it's a content-related question, it's very much likely that you can get a better answer if you email me and kind of give me a day or so, because I actually have my doc cam set up at home and I can probably record it. If you're having an issue, other people probably are as well. And I'm happy to record like particular videos where I go over examples. However, you know, you can always catch me at that time. If it's a quick question or something about the course, just know that usually I'm not going to be at a place where I'll have a doc cam there. So we might not be able to address a detailed technical question in those office hours. But if those don't work for you, you have another question, I am available to make an appointment either online or in person. Do note that if you need to meet me in person this summer, I'm going to be traveling a few weeks. So there might be just some weeks where even if I want to meet you, it's just not feasible. So in terms of the grading for the course, we're really all the assignments are going to fall into 3 bins. We're going to have 11 homework assignments. That sounds like a ton, but basically it's just dividing them on a per chapter basis of everything that we're going to cover. In aggregate, they will be worth 45% of your grade. They're not all going to be the same duration, so they won't be worth the same amount of points. For example, I think it's chapter 5. The only thing we're doing in there is the 2 sections related to Thevenin equivalent circuits. That's going to be like 2 or 3 problems on the homework. So that won't be worth as much as a particular chapter where we're doing a lot more content. In addition, we have 4 discussion board assignments. They're only worth 5% of your grade. I kind of debated about not having any of these, but we need to have a low stakes assignment to make sure that everyone's engaged with the course in the first few days. So I had to do kind of an intro discussion board that'll be due in a couple days. And I just basically put the other ones spread throughout the course that we're going to kind of use as temperature gauges or touch points to see how everyone's doing. In addition, we'll have a midterm exam and we'll have a final exam, which will be worth 50% of your grade. That sounds like it's really high stakes, and it is. I mean, that's 25% per exam. But in addition to having the problems in Connect, I'm going to give you an opportunity on those to do, well, A, you're going to turn in your detailed work. So the score you see on Connect once you take your exam will be the lowest score that you can get. I will go through and award partial credit based upon the actual handwritten work. In addition to the exams, the components in Connect, there will be a little bit of a component you prepare yourself, kind of using the simulation tools that we did in the class, and hopefully those will allow you an opportunity to raise your grade a little bit more. So let's actually grab that link for the course schedule, get it here, and then we will go here. There we go. So you'll notice that here is a breakdown of what topic we'll be covering in each particular week, along with the chapter of the book and the associated deliverables. I intentionally made your midterm exam before the 4th of July in case any of you have travel plans for that week. And you'll notice that the semester is kind of weird. It ends on July 28th, which I believe is a Thursday. So that review and final exam are going to be the one thing that aren't actually due on a Sunday. So do keep that in mind. But we're moving through a lot of stuff here. It's going to be tough, but it's going to be very, very doable, especially for those of you that are here at SAC and maybe had me for the intro course, or if you just had an enjoyable experience in your second university physics sequence and you already remember a lot of the kind of basic fundamentals that you need in order to build circuit analysis knowledge on top. And what I mean by that is if I said, oh, draw a schematic symbol for a capacitor, you could. Or if I said, state the relationship between current and voltage in a capacitor, and you said I equals C dV dt. If you have those things memorized offhand, we're going to be able to get through this really, really quick. The other thing you might want to dust up on, though, is your actual complex numbers, which many of you probably haven't used since you had like a pre-calc class. Because what we will find is when we actually analyze circuits in the frequency or the phasor domain, when we're only focused on the steady state response of a circuit, we can dramatically simplify the underlying mathematics of the analysis by representing the individual components, the passive components, resistors, inductors, and capacitors, in terms of a relationship of their phasors, which is known as impedance. So you do end up using some complex arithmetic, complex, not hard, just complex like a number with a real and imaginary part. So if you haven't done those in a while, as long as you've done vectors recently, because the mathematics of complex numbers are similar to the mathematics of vectors, because they're essentially mathematical quantities that are described by 2 real numbers. In the case of complex numbers, a real and imaginary part. In the case of vectors, a magnitude and a direction, or in rectangular form, horizontal and a vertical component. So as long as you've done one of those 2 recently and have the right triangle trig fresh in your mind, you will be totally fine. So if you have any questions, feel free to reach out. And if not, I will see you on Wednesday with our first content video and hopefully the actual textbook and homework for the course up and posted.